Okay, in this video, I'll show you how to find the horizontal and also the vertical asymptotes of this function. First, for the horizontal asymptote, remember, we have to take two limits. The first one is the limit as x approaching positive infinity of this function. And if we do get a finite value right here, then y equals to that finite value will be the horizontal asymptote. And we also have to work out the limit as x approaching negative infinity of the function, because this value might be different than that. If this is also finite, then we will have another horizontal asymptote. So for example, just like the inverse tangent x, it has two different horizontal asymptotes. But of course, these two values could be the same. So in that case, you still have one. And if the limits don't exist, or the limit is like infinity or negative infinity, then we don't have horizontal asymptotes. So we're just going to work this out first. And let's get going. First, we take the limit as x approaching positive infinity of this function, 3x minus 6 over x squared plus x minus 6. And notice this right here is really nice because we have a polynomial over another polynomial. So to take the limit as x approaching infinity, you can just compare the highest power of x on the top and the highest power of x on the bottom. And you see that this is the same as saying the limit as x approaching positive infinity. On the top is just 3x, on the bottom is just x squared. Remember, we can do this if x is approaching infinity or negative infinity, right? And the purpose of this is that we are just trying to compare the ratio of the top and the bottom, the dominating part of the top over the dominating part of the bottom. And you see that in this case, x and x squared, they can cancel, so we have only one of it. And this is saying the limit as x approaching infinity, we get 3 over x. And plugging infinity to here, we get 3 over infinity. And notice that this is just a non-infinity, it's just a finite number over infinity. We get to draw a conclusion right here, which is 0. And in this case, we see that this is finite, so we have y equals to 0 as one of the horizontal asymptotes. If this is different, then we have 2. If this is the same, we still have 1. But anyway, that's pretty much it for that part. And now, for this part, we do the same thing. The limit as x approaching negative infinity of the same function, of course. And we can still do the same thing, right? When x is approaching negative infinity, on the top, we can just care about the 3x. On the bottom, we can just care about the x squared. Once again, we are just trying to compare the dominating parts of the top and also the bottom. And this is the limit as x approaching negative infinity of 3x over x squared. And I know some of you guys noticed this is pretty much the same as that. And you cancel things out, you get the limit as x approaching negative infinity of 3 over x. And you can plug in negative infinity to here, and you get 3 over negative infinity. Right here, even though you have positive 3 over negative infinity, this is still 0. If you want to put on negative 0, that is still 0, so this is 0. And notice we have y equals to 0, so they are the same. That means we only have one horizontal asymptote, and that is y equals to 0. And this right here is it, right? And now let's talk about how we can find the vertical asymptote. And in this situation, when we have a rational function like this, what we want to worry about is we have to have a non-zero situation on the top over 0 like that. Well, sometimes you may end up with 0 over 0. In that case, it might be an open circle on the graph, namely a removable discontinuity. But when you have a non-zero over 0 situation, most likely the function will have a vertical asymptote there. So, with this said, we are just going to worry about the bottom for now, so we can find a candidate of the vertical asymptote. That means I will just have to set x squared plus x minus 6. I will have to set this to be 0. And I can solve this by factoring. We get x plus 3 times x minus 2. From the first part, we see x plus 3 has to be 0. That means x has to be negative 3. For the second part, we see that x minus 2 has to be 0. That means x has to be 2. And from this point on, you have to be extra careful. Yes, these two numbers are going to make the denominator 0. So you have to get rid of these numbers from the domain. But if you're talking about the vertical asymptote situation, pay attention to this. We also have to make sure that the top cannot be 0. So what do I mean by that? Let me demonstrate. We will have to plug in negative 3 into the original, right? Into the original and see if we have a non-zero over 0 situation or not. Let's check that out. Plugging negative 3 into here, we get 3 times negative 3 and then minus 6 over what? Over 0. Because we know if you plug in negative 3 into the bottom, it will be 0 since we just did that, right? And now you see on the top, 3 times negative 3 is negative 9, minus 6 is negative 15, over this 0 that you already have. So you know it fits this condition. So yes, there will be a vertical asymptote at negative 3. So I'll just put this down, VA right here, right? So it checks. On the other hand though, if you plug in 2 into the original function, we see that that's going to be 3 times 2 minus 6 over what? Over the 0. Why? Because you know it already, because you just solved that. But on the top, you see in this time, 3 times 2 is 6, minus 6 is 0, over this 0 that we already have. In this situation, you actually don't have a vertical asymptote. You can do a little bit more investigation, and that investigation is you take the limit as x approaching 2 of the function. And you see that you get 3x minus 6 over that, x squared plus x minus 6. And to do this limit, you know that if you plug in 2 into all the x, you end up with 0 over 0. So you simplify the expression, you see that on the top is 3 times x minus 2. On the bottom, you factor it, you get that, x plus 3 times x minus 2. And of course, you see x minus 2 can be cancelled it. And then from here, you get the limit as x approaching 2 of 3 over x plus 3. And plugging 2 now, you get 3 over 2 plus 3, namely you get 3 over 5. This right here tells you when x is approaching 2, the y value is approaching 3 over 5. And when x is exactly 2, the function is actually undefined. That means you will have an open circle when x is 2. And this right here is actually the removable discontinuity, right? So you'll see the open circle, you have a nice graph, but there's an open circle. There's no jump because the limit, you do have a left-right limit being equal to 3 over 5. So this right here, it's a removable discontinuity, right? Discontinuity like that. It's removable, right? It's not a jump, even though you have an open circle. But anyway, this is not a vertical asymptote. So be sure you just do all this kind of check. And in the end, we'll just write this down for you guys right here. For the vertical asymptote, we only have that. And you write it down in the formula of x equals to whatever this is. So just x is equal to negative 3. This is it. And in addition, if the question is asking you for removable discontinuity, this is what you do. So I can tell you a removable, write it down, removable discontinuity, right, is at x equals to 2. So yeah, that's what you have to answer if the question is also asking you for that. But anyway, This is it.